No, hi, Pam. I'm going to teach the class today.
You were on?
Oh, okay.
Hi guys, we're going to keep going with the factors that were affecting London forces. So we talked about that shape is going to be a factor that will affect a London force, and that's just that the longer and the skinnier the molecules that are interacting with one another, the stronger those dispersion forces. And all that is because there's a larger area to induce those dipoles and to have more of that polarizable electron cloud, okay, versus the really short, fat ones. Now, another factor that we left off with today in class was looking at this graph. So we can see that the boiling points here for all of the halogens and then the noble gases, we see that the halogens have a larger boiling point than the noble gases do. And that's because the halogens are diatomic in nature, so they're going to have a larger mass comparing with their respective noble gas. That means they're also easier than their electron cloud is easier to polarize. So the boiling point for a halogen is going to be a lot larger than a noble gas because these halogens have stronger intermolecular forces. So I'm going to need to apply more energy to break or overcome those intermolecular forces, which is why their boiling points then are going to be higher than the boiling points of noble gases. Okay, so let's switch gears from London dispersion forces. We'll go to dipole-dipole interactions. Dipole-dipoles are where molecules that have permanent dipoles are attracted to one another. So when we think about dipole-dipole, we're really thinking about polar covalent compounds. So right now we're just trying to piece together intramolecular forces with intermolecular forces. So when something has a polar covalent bond, we know that they have dipoles. There's a partial positive end and then there's a partial negative end. So dipole-dipole intermolecular attractions can occur based on these polar covalent bonds. So ultimately, positive end is going to attract the negative end of a molecule and then vice versa. And these forces are only important when molecules are super close to one another. So there has to be a pretty close proximity with these molecules. If we look at, so the molecule that we're looking at here is CH3CN. And on this one right here, on A, it's represented in a solid state. Try to move that, there we go. And then right here on B, it's represented in a liquid state. So I can tell the difference. So this is a really good question that I could ask you using a particle diagram. So in A, I see that there's more of a structure, they're more organized, versus in B, I see that there's a little bit more space between them and there's not nearly as much structure as there is here in A. So this would be representing the solid and that would be representing the liquid. I will represent attractive, in this picture they're representing attractive dipole-dipole forces in the red. And I know that's probably really, really hard to see. So I see that there's quite a bit of different dipole-dipole forces that are keeping that solid CH3CN together versus here on the liquid part, and again, I don't know that you can see this, but I have some repulsive forces that are being shown in blue. I still have some of the attractive, but I see more of these repulsive forces that are happening with liquids. And I can see that a lot more readily, the repulsive forces in liquids, just because they're able to slide or move past one another. Okay, so more of an arrangement here to represent solid, less of that orderly arrangement here in the liquid, and I can see attractive and repulsive forces at any instant, more so in a liquid than probably what we're going to be able to see in a solid. So for molecules of approximately equal mass and size, the strength of intermolecular attractions is going to increase with polarity. I see here that all of these, so propane, dimethyl ether, and all of their chemical formulas are written underneath. Acetaldehyde and then acetonitrile, all of them have very similar molecular weights. So we're comparing 44, 46, 44, 41. So if I'm thinking about equal mass and equal size, I'm going to look at the strength of intermolecular attractions kind of based on polarity, okay? So the more polar the molecule, the higher its boiling point is going to be. And I want you to think about why. If we kind of go back to the London dispersion forces, if I have stronger attractions, it's going to take a lot more energy to overcome those attractions. So the more polar the molecule, that means I'm going to have a stronger partial positive, partial negative charge. So because of that, because there would be a stronger attraction, because the charge will be acting as it's stronger, the electronegativity difference is greater, that means that the attraction is going to be greater, which means it's going to have a higher boiling point, because that means it's going to need more energy to try to break or overcome those intermolecular attractions. So to see that effect of dipole-dipole, it's just really easy for us to look at the boiling point of compounds that have those similar molecular weights, okay? So acetonitrile, this one here at the end, has a higher boiling point because it's just more polar than, for example, non-polar propane. So in propane, I just have carbons and hydrogens. So all of those carbon hydrogens are non-polar bonds, so the polarity of this is really, really weak. Versus dimethyl ether, which I have an oxygen group here now. Acetaldehyde also has an oxygen that's on the end, so it has more of a dipole-dipole chance. And then acetonitrile has that nitrogen, and if I find electronegativity difference there, I'm going to see that that is going to have the strongest dipole. Okay, so which is going to have a greater effect if we're talking about dipole-dipole interactions versus dispersion forces? So if two molecules are of comparable size and shape, then dipole-dipole interactions will likely be the dominating force. Okay, so if we're talking about two molecules, same size, same shape, I'm going to probably think about them as being dipole-dipole interactions. But again, I need to look to see first if there's that permanent dipole. So I'm really looking to see if there's that polar covalent bond that's there first. Then I can know that it's dipole-dipole. And then if one molecule is much larger than another, then it's going to be dispersion forces that are going to be the stronger of the two. And that's just because I may have a really large hydrocarbon chain that maybe it may have an electronegative atom at the end of that chain, so maybe like oxygen or nitrogen. But as I increase that carbon-hydrogen chain, let's say I have a really, really long carbon-hydrogen chain and then this one little small polar group at the end, dispersion forces is going to be the greater of the intermolecular attractions because I have more of those hydrocarbons than I do of that one really small little polar group that's attached at the end, okay? So much larger dispersion forces. If they're smaller in size and shape and they have that permanent dipole, then I'm going to think about it as being dipole-dipole interactions as trumping London dispersion forces. Okay, so now I just want to look at this graph with boiling point and molecular weight of some different hydrogen compounds. So this figure is going to show us the boiling points of binary compounds that form between hydrogen and then from elements 4A through 7A. So boiling points of the compounds containing group 4A elements. So if I'm looking at my 4A elements, I have CH4, SiH4, GeH4, SnH4. All of them are nonpolar and they increase systematically as I move down a group. They're going to increase, so boiling point is going to increase in comparison to molecular weight. I have a more ionizable or polarizable electron cloud, so if it's more massive, it's going to be more easier to polarize, so the boiling point is going to increase with that. If I look at the rest of these trends here, so I have my group 5A with nitrogen, I have my groups 6A here with hydrogen and oxygen, and then down here is going to be my group 7A with hydrogen and fluorine, and then again we're just following those lines with a curve according to molecular weight. So all of these pretty much follow the same trend, except for 3 of these particular atoms when they're bonded to hydrogen. And that's water, HF, and NH3. They're really small in their molecular weight, but their boiling points are much higher than the rest of these over here. So they do not follow this trend when they are bonded with hydrogen. So this is the reason why we believe this experimental data, because we graphed this, this is how we know that hydrogen bonding exists. Or at least this is how we know that when hydrogen is bonded to oxygen, fluorine, or nitrogen, that it's not going to play the same game as the rest of the elements will when they're bonded to hydrogen. Okay? So a dipole-dipole interaction experienced when hydrogen is bonded to nitrogen, oxygen, and fluorine, we just saw they're actually incredibly strong. Their boiling point is much higher than the rest of them that are graphed. So because of that, we call this a special type of bonding, which is hydrogen bonding. It is a type of dipole-dipole intermolecular force. So we can actually categorize it as a dipole-dipole, but it's much stronger than a dipole-dipole force, so that's the reason why we just separate it out and call it something different, okay? So hydrogen bonding, again, is intermolecular. So let's say, for example, I have 2 water molecules, and I see that up at the top here on the right. So the intramolecular bond is going to be, so that's the covalent bond, that's between the oxygen and hydrogen within the molecule. But the intermolecular bond is going to be between the hydrogen on this water molecule and that oxygen on the other water molecule, which you guys already know that, so we're good. Okay, if I talk about 2 hydrogen fluorine molecules, I know that interhydrogen molecular bond is between that hydrogen and that fluorine. I can see the rest of them all with the nitrogens, the hydrogens, the oxygens, and the hydrogens, okay? So one thing, at least that I want to point out, is that when hydrogen bonding occurs, nitrogen, oxygen, and fluorine, all of them are right next to one another, so I don't really necessarily know why hydrogen acts this way when it's with this really strong intermolecular force with these 3. But for us, we think that it just occurs because that hydrogen atom in a polar bond is interacting with a non-bonding electron pair on some nearby really small electronegative ion or atom. So oxygen, fluorine, and nitrogen are 3 of the more electronegative atoms that are on the periodic table. So because of that big electronegativity attraction, because of that Coulombic attraction there, we think that that's what makes them so strong. But again, we only think that based on this data here. Okay, so if we were to do some practice, it says, in which of these substances is hydrogen bonding likely to play an important role in determining physical properties? So which one would exhibit hydrogen bonding? CH4, H2 in an H2, CH3F, or H2S? I'll let you answer this one. We'll look at it together on Monday. On the next one, it says, in which of these substances is significant hydrogen bonding possible? So, and again, it says significant hydrogen bonding. So I'm looking at the one that would have the most hydrogen bonds. And then you have your 4 choices there. So answer that one. Come up with explanations as to why you would say your answer for the first one and the second one for me. Okay, and we're going to keep moving on. We already alluded that hydrogen bonding arises in part from the high electronegativity of nitrogen, oxygen, and fluorine. And then also when hydrogen is bonded to one of those very electronegative elements, the hydrogen nucleus is exposed. So like I said, we call this, it's technically a dipole-dipole interaction. So because the electron-poor hydrogen is so small, because when it's bonded to one of those nitrogens, oxygens, or fluorines, that hydrogen is very electron poor, and it is very small. So it can approach an electronegative atom very, very closely and interact with it then very strongly. So hydrogen bonds are weaker than covalent bonds, if now I'm comparing like strength of intermolecular and intramolecular. But hydrogen bonds are going to be my strongest out of those 3 intermolecular forces, such as London dispersion forces and dipole-dipole, okay? So we also said that we could, we also have something called an ion-dipole interaction, and this is what's going to create a solution. So we don't technically say that this is a type of intermolecular force, even though it is a type of intermolecular force. So ion-dipole interactions, I want you to know that they are the strongest intermolecular force. So your book, I don't think, really alludes to them. I want to allude to them because they are on your AP test. So an ion dipole, important for a solution. So let's talk about how that works. Let's say, for example, that I add salt into water. The salt is originally in a crystal. So I have a lattice that's going into water, and that crystal lattice is going to break apart. And it breaks apart because the partial positives and partial negative ends in the water dipole, in that water permanent dipole are strong enough that it can overcome the Coulombic attraction and that ionic bond that's holding sodium and chlorine together. So because of that, it's going to, all of my partial positive ends, so my hydrogens, are going to attract the chlorine atoms. And then all of my oxygen, partial negative ends of water, are going to attract and surround the sodium ions. So this is how we get a solution to form because of ion-dipole interactions. This was something that was represented to me in an AP chemistry conference or workshop that I went to. It was really important that we knew how to represent or draw the solution process or specifically solvation process. So I would want you to be able to show me that I can have my partial positive end of a water molecule attract a negative ion, and the partial negative end attract that positive cation, or the cation, or that positive sodium ion there, okay? We said before, so we have this ion-dipole interaction, and don't forget that we've talked about dipole-dipole, London dispersion, hydrogen bonding. We have this ion-dipole interaction, but we can also have that induced dipole, so which is really just London dispersion, but that induction force is really big because it can be an ion-induced one as well. Okay, so if I'm looking at butane and pentane, and I want to see which one, I'm looking at their boiling points. It should make sense that pentane would have a larger boiling point than butane, and that's because pentane has a larger mass. So because pentane has a larger mass, and butane meaning that there's 4 carbons, pentane meaning that there's 5 carbons. Just because pentane has a larger mass, it's going to have greater intermolecular attractions, which means that its boiling point should be larger. So based on what we've learned and talked about so far, that data holds true. If I'm comparing that polarizability or the strength of intermolecular forces in bromine and chlorine, so because they're both diatomics, the main intermolecular force that would be between those molecules would be London dispersion forces. The bromine intermolecular force between bromine molecules is going to be stronger than the one between chlorine molecules. And why is that? That's because bromine has more electrons, it's more massive, thus because it has more electrons, its electron cloud can be distorted more, meaning that it's going to be more polarizable. So I have a stronger intermolecular bond here than I would in here. So far everything is still, experimentally everything holds up with what we think about conceptually. If I'm looking and comparing these two, I see that I have 2-methylbutane versus pentane. It shows me here on my boiling point that pentane has a larger boiling point than 2-methylbutane. And it does because remember we talked about that area was surface area was a big thing. So because these are really long, skinny chains, I'm able to have more intermolecular forces here in pentane than I would be able to have in 2-methylbutane. So I should have to give more energy to overcome intermolecular forces here, and I see that experimentally with the boiling points. So showing boiling points and showing the structures of these is a really good way that I could just give you data and then ask you to tell me which one would have a stronger IMF and then explain why. So just to kind of summarize all of the intermolecular forces, so London dispersion forces, I can see those down here. Those are going to be the weakest. I then could have an induced dipole. So that's going to be kind of the next thing. Dipole is going to be that next one. So that's going to have that permanent dipole, so it can have that polar covalent bond. Hydrogen bonding is a type of dipole, but it's the strongest type of dipole, which is why we just classify it on its own, so that one's next. And then I have ion dipole, which is going to be the strongest one, because that ion, that full charge with that dipole, is going to have to just be the strongest because I do have that full charge. And then if it's between an ion, that's not an intermolecular. I don't even know why that's on there. It shouldn't be on there at all. But we know ionic bonding is an intramolecular force. Okay, so this is just another way that we can summarize intermolecular forces as a flowchart, but we're going to practice this, so I'm not so much worried about this right now. Okay, let's talk about how intermolecular forces affect physical properties. Thank you. The strength of the attractions between particles can greatly affect properties of a substance or a solution. So we already saw that if I have stronger intermolecular forces, the boiling point is definitely going to be affected by that. Because if I have stronger IMFs, then that means that the boiling point is going to be much higher because I have to supply a lot of energy to try to overcome those intermolecular attractions. So the strength of these IMFs is super important and dictates a lot of properties for us. And the effects of all of these intermolecular forces are additive. So the more intermolecular forces I have, the stronger the stronger that bond, or the stronger that these properties are going to feel, or that the effects are going to feel. Okay, so what I'd like you to do, so you had that one question before about hydrogen bonding. We also have this one. I want us to try to predict types and strengths. So it says list the substances that are here follows in order of increasing boiling point. So how am I going to go about doing that? I'm going to go about doing that by coming up with, we already said that the ones that have London dispersion forces are probably going to be the weakest. The ones that have that ion-induced dipole are going to be the strongest. If I think about even just ionic bonding, that's going to be even stronger because it's an intramolecular force. So think about the forces that are acting within these substances, and we want to go from the one that would have the smallest boiling point to the one that has the largest. So try this one for me, and then on the next one, you're pretty much doing the same thing. I want you to identify the intermolecular attractions present in these three substances, and then select the substance that's going to have the highest boiling point. And then we'll start with class with the first one on Monday, and we'll do this one next. You have one more practice question that I want you to try for me, please. And it's kind of just, it's an FRQ question that's summing up. It's an FRQ question that's summing up some of the stuff that we've done in previous chapters. So like writing electron configurations, talking about isoelectronic ions, talking about hybridization and molecular geometry, and then we're getting into those intermolecular forces. So you have 3 slides that I want you to try these questions on for me, please. I will see you on Monday. I hope you have a really great weekend, and if you guys have any questions on these, just post on the blog or email me and I can help you however you need. Bye, guys.